That is the features. There is no interdependencies, and that is the problem which we need to fix and address. That is critical. But if you talk about a critical complex part, there this particular scenario will be pretty challenging. So you cannot even imagine complex part with general tolerancing. So but a clearance bore gets larger and it can be further offset. So there is no medium to restrict this and fix it. The classical tool provides no means for managing feature forms. The classical tool provides no meaning for researching and refining feature functionality. Because of that, you cannot guarantee the fitment and function. And assemblability also is a question, and it will be in dilemma. So another question is, what about this particular holes? The bore 1 really bore 1? So how can you say that the bore 1 is typically bore 1? Because there is no fixed location with respect to which you do manufacture and you do the gauging and you do referenced. So what about the bore 3? That bore 3 is a bore 3 and so on. So is this a bottom of the part, or is this the bottom of the part? So is this the bottom of the part, or this is the bottom of the part? Nobody knows. We have controlled a symmetrical part in an asymmetric way. This is an absolute symmetric part, but you know the complete controls which we have done is in an asymmetric way, and the complete frustration and confusion for the manufacturing and the inspection people starts. So as a result, classical tolerancing leaves us the beholden to the tribal understanding, means a wrong understanding and interpretation method. But the GD&T, if you compare the frustration and the power of GD&T, just does the magical touch. And GD&T frustration is, the GD&T is complex. This is a myth. This is not truth. Just I will guarantee that mathematically I can explain you GD&T. So GD&T's frustration and myth, you can see most of the people, they think that GD&T is complex. GD&T is basically boring. GD&T is often used to decorate or paint your drawing rather than encode the function. They are absolutely right because they think like that. And GD&T is generally interpreted rather than decoded. They are also right because they think. And GD&T opportunities is like this. The GD&T encourages fault-tolerant design and can guarantee assemblability and function. And GD&T reduces manufacturing cost through unambiguous communication and looser tolerance. So GD&T gives you a higher tolerance so that you can play around. GD&T never only gives a loose tolerance. And GD&T turns the 3D metrology inspection system absolutely reliable in the scientific process. Let us see if we can prove that. So now the long-awaited encoding process I'm starting. The GD&T encoding process is something where the same example, again I am referring, in fact the earlier example was asymmetric. Let me intentionally do it asymmetric and do in a symmetrical way. The 6 bores serves to mutually align and locate the 6 pins, that everybody we agree. The mutual orientation and location of the bores and their perpendicularity to the bottom of the block are critical and shall be held within 0.25. If it is not perpendicular to the bottom, then it cannot be aligned. So that may be 0.2 or maybe 0.25, but it is a tighter one. But what about the location and alignment of the bore pattern? This all pattern relative to the sides. So this all we are keeping 2 mm. So this is 2 mm. So create a CAD model and forget about this general tolerancing. And most dimension will be basic. And feature inventory after creating will be using our primary reference 6 planar surface and 6 bores. Those are the attribute we have. So now the feature hierarchy we need to create that. Let us understand this. Just like the aircraft, the rolling of this part, now you can rotate this in this way or that way. Like that, you can turn this around this, and also you can turn in other direction also. So 3 different directions or rotations are known as rolling, yaw, and pitch. That means the most important feature must constrain the pitch and yaw if possible. That means you need to restrict. If you put this block over a horizontal surface plate, the one translation is restricted and 2 rotation is restricted. That is the yaw and pitch. But still it can roll. Roll means it can rotate across the plate. So that is rolling is not restricted. So how to do that? So next most important thing is to constrain the roll. So now by fixing another plane, that rolling will be as restricted. And again, the remaining degree of freedom will be restricted by the third plane. So how to do that? This is the encoding. The A is the bottom of the plate. This A, which we are seeing the bottom of the plate. And intentionally, I am giving a 2x2 chamfer here to show that a unsymmetric part can be toleranced by GD&T in a symmetric way. And earlier we saw a symmetric part by forced with tolerance in an unsymmetric way. That is the biggest headache. So encode the feature hierarchy by labeling the datums like this, and B and C. A restricts 3, B restricts 2. Just try to check this today once after going to your rooms, and you will reveal that 3, 2 and 1 degree of freedom, how it restricts. The most important feature A is the bottom of the patch, which freezes or restricts pitch and yaw. And next B, it restricts rolling, because after restricting this, it cannot roll again. And finally the third one. So add a chamfer in order to prove that intentionally I am doing a symmetric GD&T tolerancing with a non-symmetric part, asymmetric part, so that the inspection system also will be a challenging process, but here in the inspection process will be a enjoyable process. The tolerance and dimension feature now after completion will add the geometry controls. So here this bottom part we need to keep flat within 1 mm, and after that the B part need to be perpendicular with respect to A. You can see the B is perpendicular with respect to A within 1 mm, and C, the third one, need to be reference to A and B. It need to be get perpendicular with respect to the bottom part as well as this part, and that is also 1 mm. So after defining this, the CEO is this, because this is the boss, it RS3, and this is the CFO, just for a imaginary for some character I have introduced. And CTO, you can say that this is a design engineer, this is a design engineer, or manufacturing engineer, or the inspection engineer, or anything you can say. So this is not my intention is to just dramatize this. So the tolerance and datum features to complete the first 3 link of the geometry control chain, now we need to do. So flatness is addressed, perpendicularity is addressed, and then we'll move to our basic dimension. So tolerance remaining planar part, we have to go for the dimension like the 40, 120, 80 that we did. The width we have addressed this particular part. And here you can see for controlling the profile, the across the rectangular block with the chamfer cut, we have addressed it with respect to 3 different planes. The control is being fixed here and here also. So now the surface profile and 2 basic dimensions we have fixed. And now let us talk about this intermediate dimensions, where you can have different 6 tools, typical location, and this is the diameter of the holes, 20 plus minus 0.2. So what happens if I'll go for this? So position of this hole is looser tolerance, where I'm giving a 5 mm, and I'm giving a secondary control for 0.5 for axis interpretation, axis wobbling, and this is basically the whole features movement, diameters movement, and this is axis movement, that is 20. So 20.2 is the overall diameter, where 5 mm deviation is allowed, and this 0.5 is between this center to center. That means this is tighter. So in this way you can instruct and encode the whole process